Welcome to a new test and teardown video. This time it's another oscilloscope. Gould Advance model OS-255. This one is a 2-channel analog oscilloscope. It's only about 15 megahertz, and I think it's from 1978, 1979, more or less like that. And the time base can only do 1 microseconds when it's faster, but there is this pull, and then you go times 10 as fast. So that is 100 nano. So that should allow you to read those 15 megahertz. But that is, of course, the minus 3 dB pointer. As you can see here, it looks not so nice and fine. And I think if we look a little bit careful on this dirty parts here, it's actually corrosion through the aluminium because it's impossible to clean it. I really tried to clean this one. It has been standing, I don't know, in the rain or outside or somewhere with high moisture. It's just not in a very good shape. You can also see the reveal of the corrosion on the screws here. That reveals a tough storage life. So somebody saved this some 20, 30, 40 years ago and saved it somewhere not so good. So yes, I have to open this one and do a deep inspect before I can power it up. Everything moves. I did actually release a video about a year ago. That was the 255 model, much more modern compared to this one. This one is a little bit older. So yeah, let's look inside, I guess. Just wanted you to know how stuff looks like. Sometimes when I get it, I mean, can you see how dirty it is? This is the before pictures. Now we'll clean it up nice, and then I normally start the video when it's nice and clean. Inside this really old oscilloscope, and I'm not super impressed, as you can imagine. Look at that. And the corrosion here on the mains voltage switch is also not so good. And that will be time base, sweep, and obviously trigger and stuff like that. That'll be trigger level. So all that kind of stuff is here. This is also the horizontal deflection, and that will be the output feeder to the deflection plates. Power supply is neatly located here. It's not super complicated or anything, just some rectifiers, diodes, and all that kind of stuff. There's a little funny thing though. Look at the board here. It is, as you can see, full of all sorts of sticky oil, kind of. And if you look down there, can you see it's wet where I'm touching now? Here you go. Look at that. Wet and slimy. This is, of course, the high voltage output to the tip of the CRT. So quite a lot of high voltage here. So what they did is, maybe the oil is coming from that cable, so it's leaking out of that cable. So it's a part of the design or the isolation of that cable. Because look at that, up here in the other end of that cable, it looks like it's also, you know, a little bit wet and slimy. I don't know. Is that possible? It can leak from the cable? It's completely splatty. But it is a known thing that oil is a good isolator. It will remove leakage and moisture from the circuit board here, so we don't have any short circuits or any flash over. So it's probably not a bad idea. I don't think I will call this a showstopper yet. I've been trying to look for leaked capacitors and they seem to be more or less okay. I always check all that kind of stuff. It's of course pretty corroded and pretty badly nasty, dirty and all that kind of stuff. Look at that. No, it's just dirty. So that's time base, PZ board as you, yes. Here is channel 1 and channel 2 inputs. And I think this one is really funny. What is going on in here? Oi, 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 oi. We got 2 transistors mounted together like that. A little temperature compensated balanced amplifier, right? And then this neatly little isolation tool for temperature compensation. Fantastic. But why? Oh, there's also one here. And this is of course missing on that channel. Interesting. And a little copper isolator in the between here. And wow, that is some nice design. Oh, no, look what that is. Can you see the little copper isolator? It looks like it's an isolator and it goes up in between the 2 transistors. I bet there's a little heater on the other side of that circuit board or a power resistor or something like that. Or what have you got here? Oh, there's no way I can get in there and have a look. I need to look at that on the schematics. By the way, I found all the schematics on radiomuseum, so I'm definitely gonna go and zoom in on that area. I think that is interesting. And look at that, what we also got here at the front end. See, you can have either a little IC, an 8-pin IC, or a dual field effect transistor for that input stage. So that is looking quite nice. I also expect to somewhere here find some diodes, probably those, or sometimes you see 2 or 4 diodes. So we have a chop or alternator because it's a 2-channel scope. And then we have a high power output drive system for the deflection. And that will be the deflection transistors and the voltage drop resistors. And they, of course, drive really warm because we have high voltage and high bias current. So this one can run quite fast. And look what they're trying to do with the wires here for the vertical deflection. They're trying to keep the impedance quite high and don't connect to all sorts of stuff. It's just hanging like that. I don't find a delay line or anything like that, but of course this scope is not designed for super fast pulses and stuff like that. So yeah, I think I do dare to power it up the way that this looks. It's okay, kind of safe, but I want to have a wire for the chassis for self-protection. Here is the schematic of the input circuit. As you see, first we have the classic attenuator, not a big surprise there. Then we go to TR 212 and 213. Now we're looking at channel B. That will be the dual FET. They draw them as 2 individual transistors in the schematic, but that is of course not true. It's a 2-in-1. The next 2 transistors in the schematic That will be TR 222 and 214. That will be the temperature matched NPN-PNP pair. And that is definitely because they don't want any DC drift in this in those two transistors for a nice and stable readout. If we look a little bit more to the right in the schematic, we can here see channel 1 and channel 2 and the diode system that is used to select 1 or 2 and do the chop modes. And there is a little oscillator, the chop oscillator at the bottom part right here, and then 2 diodes that selects channel 1 and channel 2. So we got select diodes and we have signal through diodes in this system, and then we have a final output amplifier that is of course only one that is driving the scope deflection plates directly. One thing that comes to my mind when I've been poking around here with the front panel is how do you select 1 or 2 channels? I mean, it looks a little bit like both of your channels, they will be on all the time, right? Because I don't see a channel 1, channel 2 kind of thing. I see this is the trigger, right? So you can positive, negative on channel 1 or channel 2 or external trick. So, and then you have the trigger level, right? But there's no channel on off. I don't understand that. So this is a 2-channel scope always, right? How do you change between alternating or chop mode? So this is probably just automatic or always. I don't know. Let's put all the dials here in the middle, and let's just crank on mains like that. It's using 50 watts and 40, 30. I have my finger here on the switch. 30 watts is quite normal. I would expect to see. Yes. Look at that. We definitely got a signal. Why is it? Okay, so no need to no need to be so afraid. Okay, let's turn on. Here we go. That is channel 1. Trigger. Can you not? What am I doing wrong here? So channel 1 is a little bit dodgy, isn't it? So this is channel 2. Okay, I am in channel 2, so that is me being a complete jerk here. Look at that. This is channel 2. I am triggering now on channel 2. Level, doing everything right. So channel 2 seems to be good and stable. Oops. Did I say that a little bit too fast? Okay, channel 2 is good. Let's play a little bit with channel 1. Okay, and then we go trick. Okay, trigger works, but you can see it's sailing. All I have to do is just work those pots, baby. And there you have it. A perfect, stable, and reliable. I don't know. I wouldn't say that. Oh, that is pretty nice. But this thing works. I mean, really? I want to play a little bit with this and see if I can clean up everything, get it a little bit better. Maybe I can figure out why it is so unstable. I think the idea is both channels they're on. So now I'm playing with channel 2. So if you don't want channel 1, all you have to do is just dial it outside of the screen. And there you have it. one channel is now on. I think that's just how you do it. There's no other way as far as I can see it, right? So what I want to do is I want to adjust the level to 100%. So this is a 1 kilohertz signal. So I should... Oh, this is just not my day. Look at that switch. So this is the... That's just absolutely full of loose connections. Oh man, oh man, oh. Not... Okay, so that the variable here is just not... Hello. All right, let's continue. Channel 1. And now the variable, see? Variable works here in channel 1. So I think this is the 100%. So what I want to do is I want to dial frequency up until I get the 90%. You have the dotted lines here and here. So this is the 3 dB point. So like I said, 1 kilohertz, let's go to 10 kilohertz. And then tick, tick, tick. And there you have it. And then we just go up a factor of 10 each time. So that is 100 kilohertz. Again, exactly the same. And that is 1 megahertz. Now it's going to be... Oh, I don't have any more here, right? So now what I want to do is I want to... Yeah, 1 megahertz is 1 microsecond. And 1 microsecond here, that means... I don't know if I can show you this. How easy is that to see? I don't know. But something is wrong with the time base, right? Because 1 microsecond and 1 megahertz, that should have been 1 full sine wave per division here. And this is not what I see. I see it's about 2 and something. So time base is a little bit off here, right? Oh, it's because I have... Oh, dummy. Here's the calibrate. Ay, 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 ay. Now it's getting bad. Because it's difficult to read this here in the shadow. It says cal here if you really look careful, okay? But there's no clickety-click or anything. So here you have it. 1 full curve here per... Can you see that? I don't know if you can see that. But that means time base is okay. And if I pull this... it goes times 10. And then we are back here when we're 10 down, and then we can do it again exactly the same. All right, so good. So far, so good. So now we have 100 nanosecond per division, and we still have this a little bit unstable behavior. So we're still 100%. Let's crank up the frequency. 1, 2, 3, 4, 5 megahertz. 6, 7, 8, 9, 10, 15. And, okay, here you go. That is 20. Let me take, and yeah, okay, here we go. 23 megahertz. And that is what it is capable of doing today. 23 megahertz. That's pretty cool. So now I will just go and clean up everything and hopefully get this little bit unstable behavior here. I want to get rid of that. Somebody should give me royalties from this Contact Kimi company. As always, this Contact 61 is just magic. Look at that. Here you go. And then the clickety-click is also working. Haha. That was super easy. On some of these contacts here, you have a little hole. I should probably show you this. This little potentiometer here. There's access down here to the contacts of the potentiometer, and here this black piece on the back. There's between the black plastic and the metal casing here. There's a tiny, tiny little hole where you can spray in. And then it will get into the contacts and clean them and lubricate them and all that kind of stuff. And it is actually that easy. I did exactly the same with it. These are actually open, so they are easy to fix. So like new. Haha, until now. Okay, brilliant. I don't know if I should give up and find another job. Because look at that. I think this color here in the shadow here is just impossible for me to read for whatever reason. I don't know. I think it is possible to see this on the video, but in real life, it's just not easy to see. But down here it says off. So that means when you dial one of the channels out of the screen and then click, that channel is now turned off. However, it is not changing anything at all because it is already out of the screen. And the fun thing is that if you check out brightness real careful, there's no change, there's nothing. All it does is it pulls this out of the screen and then the click is just for fun. It's not doing anything whatsoever but saying click. See? Not a damn thing. Now it is. Now it comes. This is what I wanted to see. Aha, so we have a problem with that switch as well. This is exactly what I wanted to see. I wanted to see the screen getting more bright when this channel is off. So now it happens. Okay, thank you. So those switches just needed a little bit more massage. And now, of course, this channel is on. Now it is still on and now it's off when the other one gets more bright. So it is actually doing something when the switches are working. And this is also what I should be able to see here. It is working. Because I also put in some contact 61 in those, but I didn't massage them yet. But that is how it is working. And it is getting more and more nice and stable. As you can see now, the curve is not getting up and down. And all this is also nice and fine. And then it goes click and stable. So, I mean, this baby is from, it's, what is it, 45 years old. And still kicking after a little bit of cleaning. So I think I'm done playing with this fantastic old oscilloscope. Thank you very much for watching, and please come back again soon. Bye bye.